Thank you all for joining us. We're just going to wait a moment while the folks join us from the waiting room. As you join, you'll see a poll. We'd love for you to tell us a little bit about yourself, and then we'll get started in about 30 seconds. Great. Well, welcome everybody, and thank you for joining us today, and welcome to our second webinar for our LunaRecycle Challenge. My name is Chris Frangione. I am the acting program manager for the LunaRecycle Challenge. So today's webinar is going to be focused on the promise and application of digital twins for NASA. Today's webinar was originally scheduled for 1 hour and 15 minutes, but due to having 4 amazing speakers, we are extending it to 1 hour and 30 minutes. We hope that you can stay with us and apologize for the last minute change. So first, some quick housekeeping. Today's webinar will be recorded. So if you are unable to join us, if you are unable to stay with us, we will have it as a recording. We will post the recording on our LunaRecycle website that you could see in the lower right-hand corner. We'll also share that website again with you at the end of the webinar. And that although you will not be able to turn on your video or microphone, you will be able to ask questions of our presenters using the Q&A function that's at the bottom of your screen. By using the Q&A function, we will have a record of all the questions that were asked. We may not be able to answer all of them during this webinar, but all questions that are relevant to the challenge itself will be answered in writing and put in our FAQs on that website. An important caveat for today is that we have these 4 great speakers. The opinions that they are sharing are theirs alone. They are not specifically related to the rules of this challenge, nor are they meant to give you specific direction on how to participate in this challenge. They are their opinions only. For all rules and eligibility and everything else, the official policies are on that LunaRecycle website. You'll see a couple of polls pop up during this webinar, one that's up right now. We ask that you do answer these questions because it provides us with important information on what you are interested in and how we can best support you as a potential solver. So we'll quickly go over the agenda, and then we'll get into the meat in it. So we'll do a quick refresher on the LunaRecycle Challenge, what it is, how does it work, and some key dates. And then we'll really focus heavily on the digital twins. Then we'll get into our 4 amazing speakers. They will all present, and then we will start answering the questions that you put into the Q&A function. So you can put your questions in at any moment in time during their presentations, but we will not get to them until all presentations are completed. So I'm going to do a quick bio of each of our presenters so that you know who they are, and then we'll dig in. Our first presenter is John Vickers, who serves as NASA's Principal Technologist for Advanced Manufacturing. He serves the Space Technology Mission Directorate at NASA headquarters and as a senior leader at the NASA Marshall Space Flight Center. He's also the Associate Director of the Marshall Materials and Processes Laboratory and the Director of NASA's National Center for Advanced Manufacturing. In these positions, John provides agency-wide leadership for technology investment strategies and is the principal steward of the agency's advanced manufacturing technical capabilities. He has over 40 years of experience in materials and manufacturing related to research and development, engineering, and production for propulsion, spacecraft, and scientific systems. He serves as the NASA representative on the National Science and Technology Council's Subcommittee on Advanced Manufacturing, the Subcommittee on Critical Minerals, and the Digital Twins R&D Fast Track Action Committee. He's a fellow of SME. Dr. Michael Greaves is an internationally renowned expert on digital twins, a concept that he originated, and organizational digital transformation. His focus is on product development, engineering, systems engineering, and complex systems, manufacturing, especially additive manufacturing, and operational sustainment. Dr. Greaves has written the seminal books on product lifecycle management and the seminal papers and chapters on digital twins. He has consulted and/or done research at some of the top global organizations, including NASA, Boeing, Unilever, Newport News Shipbuilding, and General Motors. So we're very excited to have him also. Dr. Jan Vandenbrand is the Senior Vice President of the Future Concept Divisions, formerly known as Xerox PARC, that was recently acquired by SRI. Before that, he was a DARPA program manager, a technical fellow and a senior manager in Boeing's Applied Math Group, and started his career automating machining for Unigraphics, which is now part of Siemens NX. During his career, he focused on creating computational tools to advance design and manufacturing with measurable impacts at all the locations he worked. He brings a vast amount of practical experience on what works or not and where exciting new challenges are. Again, super grateful to have Dr. Vandenbrand with us. And then Keith Foston manages the battery solutions department at Siemens, developing applications to improve the production quality of battery gigafactories in North America. The digital thread through his career has been simulation and high-performance computing, from Oscar-winning movies and Formula One teams to advanced manufacturing. And we're very lucky to have Keith with us today also. Next slide. So we're quickly going to do just a very brief refresher on this. We did a whole webinar on what the LunaRecycle Challenge is. You can see that on our website. The recording is on there. But we just want to remind everybody here today what it is that the LunaRecycle Challenge is. So as a reminder, the LunaRecycle Challenge is a $3 million, two-track, two-phase competition focused on the design and development of recycling solutions that can reduce solid waste and improve the sustainability of long-term missions for NASA. Our phase 1 submissions are due March 31st, 2025. And for more information on rules and eligibility, please visit our website. All that information is captured there. Next slide, please. There are 2 tracks in the LunaRecycle Challenge. Solvers may choose to participate in one or both of the tracks. In the prototype build track, solvers will ultimately develop a working prototype of a recycling solution. In the digital twin track, solvers will ultimately design a digital twin of a complete system for recycling one or more solid waste categories on the lunar surface and processing one or more end products. Again, you can find all the details on the LunaRecycle Challenge on our website. We know that that brief overview was extremely brief, but we want to get into the meat of today, which is a deep dive focus on digital twins. And as a reminder that we said earlier in this, these are the opinions of these 4 speakers. They are not specific to the rules of this challenge, nor should they be taken as a direction that you should take if you participate in this challenge. They are just to provide you with what's going on in the world of digital twins. So I'm now going to pass this off to John Vickers to start us off with the presentations.
Hey, thank you, Chris. And good afternoon, everyone. First, let me thank Chris and the entire Centennial Challenge team. I think this is going to be a really exciting webinar, and a special thanks to our other participants today, Mike and Keith and Jan, for their considerable expertise. Let me make a couple of comments about digital twins before we get started. I know sometimes the term digital twins can sound a little bit like sci-fi, but it really does have some practical application. Some of it is a little bit sci-fi, but I think as I go through my charts, and I've got a lot of charts, I'm going to talk really as fast as I can, and I'm not a fast talker. So next chart, please. I'm not going to play this video. Sometimes in my talks that I give on digital twins, I do play this video, but I'm trying to illustrate a point. I don't really have time today. It's a you can find it on YouTube. So I encourage you to go look for it. It's from 1994, and it's a clip from the Today Show. And Bryant Gumbel makes this uh, comment to Katie Couric about what is this internet anyway. And so what I want to illustrate is that was 30 years ago, and we have all seen the transformation associated with the internet. So that was a tipping point back then. And I think we're at that same sort of a tipping point for the tools that we're seeing today. AI is one, but digital twins is certainly another. And I really think that we're at more than just a tipping point. I think we're at an avalanche point. I don't think the next 30 years will be the incremental advancement that we had from the internet. I think it will be an exponential advancement. So next chart, please. So I am going to play this video, Elisa, and but there's what I want to say about it is it's a display at a museum in London, and I want to point out the realism. It's just I haven't been there, but I think it would just be amazing to be in this museum scene. It's taken from a painting. You see the painting, a Rembrandt painting on the left. And it's not a digital twin, it's a video. It's a very complicated video, but it's what I envision digital twins to be in the future when we can put the physics in concert with the simulation that you just saw. So next chart, please. Like I said, I'm gonna go really fast. So you hear an awful lot about digital twin definitions, and you see the footnote at the lower left. There are hundreds, probably more like thousands of digital twins definitions. I sort of subscribe to the Humpty Dumpty comment that you see about middle left there. When I use a word, I mean it. It means just what I choose it to mean, no more, no less. Also, I really like this comment from Da Vinci. A poet would be overcome by sleep and hunger before being able to describe with words what a painter is able to in an instant. Jump back up to the top. There's a recent National Academies report that I'll mention in a minute, and it has a definition to open its report that's becoming somewhat widely accepted, and that's fine. I'm not worried about definitions. You should not worry about definitions. There is no authority that says what a digital twin is or is not. And particularly, this definition suggests that there must be a physical artifact to correspond to the computational. And I just don't believe that's true. And in fact, this competition that we're in, we expect many digital twins to be produced, and we would not expect many of those to go forward and to be actually physically manufactured. Now, when I'm pressed, I can give a definition. And a couple of weeks ago, a team that I was on asked us to put together definitions. So I put the one together at the lower right. And in parentheses, I put some of the attributes that I think are important to a digital twin. However, I think it's still unsatisfying and unsatisfactory to me. So next chart. There is a lot of national attention, international attention on digital twins today. And so I encourage you to go take a look at the National Academies report that I mentioned earlier. Just came out earlier this year, I think maybe February of 24. And it addresses research and technology gaps, something that we're interested in for digital twins. That prompted a committee to be established by the National Science and Technology Council, and I'm serving on that committee. And what we're doing is putting together a national strategy for research and development for digital twins, and that should be published in the spring of next year. Next chart, please. NASA also has interest in digital transformation entirely. And so we have a formal strategy, and this chart is from that formal strategy. And you see these 5 elements of our digital transformation strategy. I sort of focus on the targets, the number four targets, and then the 6 technology foundations. And digital twins is one of those 6 technology foundations. Next chart, please. So this chart goes a little bit deep, one step deeper into the content of those 6 technology foundations. And so you see digital twins on the right, and it's my opinion from these arrows that I've drawn that it integrates or assimilates the information from these other tool areas, and it's the complete picture. It's the beginning and the end, so the complete picture. Now, if you want to understand the importance of something, I always say follow the money. And if you look at market projections for these individual areas combined in 2030, they will exceed $1 trillion. I think that's a low estimate. I think they've underestimated that, and in fact, I think there's likely to be single companies worth $1 trillion, and maybe even our first trillionaire in these working in these areas. So next chart, please. All right, so I'm gonna go through several examples just to give an idea of the kind of work we're doing at NASA. First is this Lunar Recycling Centennial Challenge, this $3 million challenge. I happened to be in attendance when our deputy administrator made some comments about a year ago. She said, everything that we do on the moon, we've got to figure out how to dispose of it or it's there forever. That is particularly true. We've had about a little over 100 missions to the moon since the 1960s, and there's 500,000 pounds of stuff that we've left there with no plan to do anything with it until we figure out, and you guys help us figure out how to recycle it. I think a digital twin approach to this gives us much more potential for solving these problems where we really don't have good ideas today. Next chart, please. So here's another one. This is another area that I work in. It's a digital twin for qualification and certification of additive manufacturing. Today, we do that entirely empirically. And so we have a grant. It's a substantial grant, $15 million over 5 years, to try to make progress with a computational approach, a digital twin approach, to look at things like materials, process, structure, properties, because that's what we try to do empirically, is to develop those relationships. We're not able to do that today. This is one of those things that we don't have the computational capabilities to do, but we hope this makes significant progress towards that, because today's approach costs too much and takes too long. Next chart, please. So here's one, our Michoud Assembly Facility in New Orleans, where we build the NASA Space Launch System rocket. It's a very complex operation, more than 1,000 suppliers. The rocket has more than 1 million parts. The factory is more than 40 acres under one roof. So it's a very complex operation. We have the software capabilities to build digital twins today. We're not able to because of legacy and culture and and cost, those kinds of barriers, but we are able to do that today. And I think for these kinds of operations, if you don't take this approach, you'll obsolete yourself in the future. Next chart, please. So I'm gonna skip this video. I know I'm running short of time, but this is a test of one of the that rocket, that SLS. This is the hydrogen tank. We tested it to failure. You can find this video as well out on YouTube. We were able to predict within 3% the failure load of this tank. And so my question is, at what point do we not have to do these very expensive, maybe $100 million tests? We're able to do it computationally. You see the quote that I've used many times in my career from von Braun: one good test is worth 1,000 expert opinions. Now my question is, how many thousands of simulations is worth one good test? Next chart, please. So here's something really exciting. How do we explore the unknown? This is about the James Webb Space Telescope that's operational today, that's bringing back these tremendous images. And you see the link at the lower left. that's an MIT Technology Review article that you can read about how we're using digital twins. But the real potential out there is for exploring the unknown, looking at unexplored locations and understanding the unexpected. That's the far out sci-fi future that I see for digital twins. Next chart, please. So here's another area that we're not quite possible computationally. We're looking at Earth systems. So Earth weather, Earth oceans, those kinds of things. They've put together a program that uses these questions: what now, what next, and what if, to look at those Earth systems. And like I said, we're not quite there computationally, but we're making tremendous progress. So next chart, please. Now we're at the very beginning of building lunar outposts, those kinds of things. And we're doing that, I'm afraid, in the silos that we have naturally done it before. And so we're advocating, and we have some planning projects to look at digital twins to manage all of that infrastructure: power and comm and crew and habitat construction, all of those kinds of things. And I think that's my last chart. And appreciate looking forward to the discussion later on. And I think it's my pleasure to turn it over to Mike Greaves now.
Thank you, John. Great presentation. A lot of good stuff there. I am going to share my screen. First, I'd like to say welcome to everybody. I see that we have people from all over the world, so I won't say good morning or good evening or whatever, but certainly welcome to this presentation. And I'm going to share my screen here. So is my screen up?
Yes, it is.
Perfect.
Okay, thank you. So welcome to the LunaRecycle Challenge webinar. And I'm going to, in this very brief period of time, I'm going to give a kind of a little overview of both product lifecycle management, which is implicit here, and the digital twin, and looking at what we can do with this digital twin today. And I am absolutely in agreement with everything John said about the fact that this is an explosive area. When John and I started this, digital twins were probably related to aerospace and automotive, and subsequently I'm seeing digital twins in pretty much every industry and aspect of life that you can imagine. So I think that you're going to see and continue to see an exponential increase in the kinds of capabilities, and I'll spend a few minutes telling you why. But first, I wanted to talk a little bit about the overarching area here, because it has application to what we're talking about. And this is the digital twin product lifecycle. And in fact, the digital twin didn't even have a name to begin with. It was the underlying premise of product lifecycle management. But what this is showing is we now have a product-centric perspective of our objects and things and products, where we used to have a functional perspective. And John just alluded to that in terms of having silos of information. What we really want to do is to populate and consume a central source around a product lifecycle. And I divide the product lifecycle into kind of these simple areas. We create the product, we build the product, we operate and sustain the product, and then we dispose and recycle the product. With respect to what we're talking about on the moon, while I certainly believe in being a good steward of the environment, our issue up there is not going to be that we can't find places to put our disposed of product. The issue of it is that pretty much everything currently that we have up there, we have to bring up there, which is very expensive. So if you look at this sort of product lifecycle perspective, we want to recycle as much as we can, because it's a continuous loop. We go from dispose, recycle to creating products. And so the more that we can recycle and put to reuse in the moon environment, is going to basically dramatically decrease the amount of cost of having to ship up there. UPS charges a lot to ship to the moon, and we want to make sure that we can recycle as much as we possibly can in order to be as efficient and effective as possible. And if you're interested in more of that, you can see my first book, which I have listed down there below. John is absolutely right. The definitional aspect of digital twins, and in point of fact, the last time I looked, there were like 500,000 definitions. Some were duplicated, but there's a huge definitional issue with digital twins. And I always liken it to the parable of the blind man and the elephant. Depending on what part of the elephant they were touching, whether it was the tusks or the hide or the tail, they described it differently. And I think that with the idea that a picture is worth 1,000 words, the digital twin model is really what we want to be able to use in order to understand what the digital twin is. And in essence, it has three major components. Over on the left side, you see the physical objects in physical space, and we've had those in time immemorial. The issue has been that we wanted to think about something new. It had to take physical form immediately. We had to do a drawing, blueprint, build a prototype of it. And so we were very limited when we came up with new ideas. It was very expensive to translate those into actual physical products. On the right side, we have what I call virtual space, which is digital space, and it contains not only the digital objects that we have corresponding over in the physical world, but it also has the environment which those objects operate in. Initially, we just started off with the object itself, but now, in fact, we're using the term metaverse. And in fact, John and I participated in a book that just came out called Digital Twin Simulation in the Metaverse, in terms of talking about having metaverses that will allow us to have not only the geometry of these things, but also how they're going to behave. The third aspect is connecting between them, and it's bi-directional. We have data that comes from the physical world because, quite frankly, if we don't have what's happening in reality, the data of the physical world, we can't have a realistic digital twin that will replicate and predict what the future holds for us. And then what we want to do is we want to use information and data in order to be able to move that work that we're going to do over in this virtual space into the physical world. And why do we want to do that? We want to do that because in the 20th century and before, all our work activity, as I just said, occurred pretty much in physical space. As soon as we had an idea, it had to take physical form for us to share with other people. We want to move that work activity in the 21st century, which I really think we ought to call the third millennium, because we can substitute information that we generate over on the right-hand side for wasted physical resources in doing goal-oriented tasks that are over on the left-hand side. We actually have to expend physical resources to do physical things in our real world, but to the extent that we can do all our planning and checking out as to whether these things are capability, and as John said, the testing in the virtual space, we can basically save tons of time, energy, and material, and especially elapsed time, which is what the clock runs on us, that is our most precious and valuable resource. We can never recover, as the clock ticks forward, we can never recover the past. So this three elements of the digital twin model is really what we're focused on. And it takes precedence over anybody's definition, including my own and John's, as to what a digital twin is. So I like referencing the model as opposed to word definitions, because I think word definitions invoke what you already know, but if you don't understand what it is, you need models that look like this. I want to briefly run you through the digital twin types. And as you can see, it basically ties back to the product life cycle that I talked about initially. The first thing we have is a digital twin prototype. So this is basically the idea that says as soon as we have an idea and we're going to actually manufacture it, we have what I call the prototypical digital twin. And what this means is the digital twin exists before there's a physical object that is going to exist. And so even though you're basically doing what I would call a digital twin prototype, the whole idea is it has to have the ability of being realized in the physical world. If it isn't, it's just pretty pictures or an animation, but your whole purpose here is going to be creating something that actually could be made when we basically follow all the plans. So these are all the products that can be made. And this is not only the drawing and engineering capabilities and things like that. How do we actually make it? What are the means of production? And we have to have those two things, what we're going to make and how we're going to make it, in order to be able to have a digital twin prototype. When we start to make things, and I'm talking about complex systems, not simple things, we want to have, as we make this, a digital twin instance. And this digital twin instance gets connected to its physical counterpart and exists throughout the entire life of that product, from the time it's built and rolls off the assembly line till it's disposed of. And in point of fact, the digital twin has an advantage because products wear out. The digital twin instance can continue on in perpetuity. So instead of just losing all the data we have with respect to our physical object, we basically will be able to have that digital twin in existence for as long as we need it. And so these are the individual products that are made. Finally, and this is where it really gets interesting, is this is the digital twin aggregate, which if we basically look at all how they perform, the population of them, we will be able to do prediction of what is going to occur, because when we see certain sensor readings, we are going to be based on our digital twin aggregate, know or at least have probabilities of what's going to happen. So these are all the products that have been made. So in terms of scope and scale, we're basically seeing all kinds of things: automotives, mining, and now mining on the moon, power generation systems, airplanes, ships, oil platforms, digital twins of smart cities, of people from a biology standpoint, not how they behave. Pharmaceuticals are developed this way. And then, as you heard, a digital twin of the Earth, which we really have a long way to go on that, because it's the most complex system I think we have in the universe. But we're also going to have digital twins of intangible things. So because of humans, if we can visualize in our own minds, we can have a digital twin of it, even if it doesn't take physical geometry. It's going to have a presence in terms of the use of physical resources in the world. And so logistics systems, the process industry per se, I've seen it on entire economic systems, manufacturing processes, and then supply chain, or what I call the supply net, which is the virtual counterpart of these products. And so not only I had the idea that we could have intangible products to begin with. This was such a new concept that we only talked about tangible products, but clearly we can have intangible things like shown here in terms of our digital twins. And with that, I want to thank you, and I'm going to turn it over to Jan and stop sharing.
Well, thank you so much, Mike. I'm waiting for my presentation to come up. So I'm not presenting. Chris, can you bring it up again? Excellent, thank you. That's not mine. You have to go back or front. Well, while Chris is looking for the correct presentation, I would like to start with a story. So whenever my daughter was a teenager, she was 12, we would sign her up for summer classes. And one of the summer classes we signed her up for was a robotics class. And in that robotics class, she had to design and build a robot. And one day, after picking her up, she turned to me and said, "Dad, nothing ever works." And she says, "Look, all these components work, but as soon as I put them together, it doesn't work anymore. And I think what her observation is the essence of what we're trying to do with digital twins. In any case, my name is Jan Vandenbrand. I'm the head of future concepts at PARC, which is now part of Stanford Research Institute. And I'd like to talk to you a little bit more about facing, and I'm hoping to inspire future.
Hey, Jan,
Next slide.
have to-
Okay, thank you.
You're okay for now. You might have to switch to your phone. We'll see how it goes. You're good for now.
Yeah. Okay. I may, because I'm having challenges with my internet, I will temporarily switch off my video. Let me know if you can still hear me.
You're great for now.
Okay, good. Hopefully this will help the bandwidth a little bit. And so whenever I was at DARPA, we had a closer look on why it's so hard to build something that works the first time. And we had a closer look at the V22 development. We also looked at other major development programs. And one of the things we found was that unanticipated problems were one of the major causes of major program overruns. And if you look at the timeline and the original cost estimate of the V22, you will see that the actual program ran over by a factor of 2, both in cost as well as time. And when you look at what some of the causes were, they all stemmed back to unanticipated problems that required major redesign very late during the prototyping or pre-production stages. Unfortunately, it also caused a number of people to lose their lives. And so obviously this is something we don't want. And the question is, how can we do better than this? And as I mentioned earlier, this is not unique to the V22. Any major program has had similar problems. And all of these suffer from the same problem, that there are major cost and time overruns. And obviously, whenever we're in space, whenever we're on the moon, we really can't afford to do this. And the question is, how do we get to first-time quality? And so whenever you dig a little bit deeper, next slide, please. And so whenever we looked a little bit deeper into it, and there's actually an interesting RAND study that looked into this, and their conclusion was that the cost overruns are driven by complexity. And one way to deal with complexity is to silo the development as well as the design and development of these things. So what you see in the middle here is the wheel well of a P8 Poseidon. And you will see it has mechanisms, it has electrical, it has hydraulics, and all of these are designed by different groups of people. They use different systems. And the problem is, none of these different disciplines are connected in any way. Trying to connect them is very challenging. It often exceeds the capabilities of the systems. And the consequence is that we really don't understand how different components will interact with each other. And so the question is, how can we do better? And if you think, well, humans can think about it, well, actually, no. The complexity of our current systems is so high that no one person can actually wrap their head around everything that's involved. Let's go to the next slide to give a more precise example of what I mean by unanticipated problems. Let's suppose you have a set of wiring, and let's suppose you have a turbocharger. Now, the people who designed the wiring bundles, they simulated all the electronics, the people who designed the turbocharger. They simulated the primary function of the turbocharger, which is to compress air to improve the efficiency of, let's say, a combustion engine. But the problem is that all of these components have side effects. And so, for example, the turbocharger, it makes noise, it vibrates, but it also gets really hot. And if you happen to route the wires close to the turbocharger, it may actually melt the wires and create a short circuit. And if you look at the right-hand side, that's actually a picture of a wiring bundle in my car, where the insulation, the heat shield basically had fallen away, that melted the wire and created all kinds of problems. And so the issue is that we tend to simulate the primary functions, but we really don't accommodate all the side effects and the interferences between all the different components that are nearby. And so that is one of the major challenges that I would like the community to start thinking about. How do you model, how do you represent digital twins so that you can find side effects, the interactions between all of these components? Now let's go to the next slide. And I would call this the Hello World modeling channels for digital twins. And you see, if you look at the picture on the right-hand side, you see two pendulum clocks. And these were actually designed by Christian Huygens. He was a Dutch mathematician or a Dutch scientist. And he designed very accurate clocks for navigation, for ship navigation. And one of the things he discovered, and typically what they would do is they would mount two of these clocks on the same platform. And one of the things they discovered was that these pendulums would synchronize. It took about 300 years to explain this phenomena mathematically, which means that there was some kind of communication between these clocks that influence each other. And so my question to the whole community is, well, if you didn't know about this potential side effect, this potential interaction, how would you model your clock so that whenever you compose it, you would discover this behavior? So in other words, how do you represent a digital twin of a component, let's say, so that whenever you assemble it into a larger system, you can discover these side effects, these influences with each other? And so there are major challenges in how do you represent something so you can discover this? How do you compose digital twins? I don't think we really know. Is there any mathematics that can describe behavior and describe or discover emergent behavior? So whenever we were at DARPA, we looked into algebra of operads, category theory, sheaf theory. There's some promise there, but there's also a tremendous amount of work that still needs to be done, because keep in mind that you have to cross multiple physics. Now, there are also other approaches from computer science that could provide an answer. Things like qualitative physics, which is something that was developed at Park. In other words, how do you reason about physics without actually having to perform complicated computations? And it's something that humans do on a daily basis. You put a flame underneath a pot of water, the pot of water will get hot. That's qualitative reasoning. And you may get a long way in understanding how things behave. But it also asks a question, or it also poses another challenge. We can probably build these digital twins by hand, but it's way too expensive, and it will take way too much time, which basically means it's a non-starter. However, there's a lot of information around. And so the question is, how would you build a digital twin builder? In other words, how would you build a digital twin compiler so that you take away the human effort? And so in any case, there are many challenges, I think, that still need to be answered. I'm trying to interest a number of funding agencies. So we just came back from a Department of Energy and an NSF workshop where I'm trying to influence as well as gain interest so that we can start putting some funding towards trying to solve these problems on a more general scale. But in any case, I believe it. Next slide. No, that's so in any case, yes, thank you. This is so what I believe the impact, at least for terrestrial development, is if we had true virtual prototypes so that we can find unanticipated the design cycle to build very complex products and assure first-time quality. But again, a lot of work still needs to be done to be able to achieve this vision. So this is not a short-term solution I'm talking about. What I'm talking about is a research agenda towards getting towards that goal. But I firmly believe this will have significant terrestrial benefits, but will be essential for anything we do in space. Next slide, please. In any case, I added the Heilmeyer Catechism. For those of you who work with DARPA know that you have to be able to give a very crisp definition of what you're trying to do. And this is my my short synopsis of what I think it will take to create a program around building digital twins so that we can discover unanticipated problems and essentially avoid major program overruns and assure first-time quality. So once again, thank you so much for listening. I believe this is my last slide, and I would like to hand this over to the next presentation, which is Keith from Siemens.
Thanks, Jan. Appreciate it. It was great to see you with the Department of Energy a couple of weeks ago, where digital twins are really important in terms of trying to get things right the first time and improve quality in particular. So my slides should be coming up here in just a moment. But Keith Boston, I actually work as the manager of battery solutions at Siemens here in the US. We're a huge global company. You probably recognize the name if you've been involved in kind of certainly in Europe, looking at the power sector, for example, wind turbines and other things. But what you might not know is that Siemens has a whole division that is dedicated to providing tools to generate digital twins that's used a lot in industry, right? And I'm going to give you some examples today from the space sector. And I guess, as everyone on the call has said today, we should really be trying to launch before we build. I see that Jan, for me at least, Jan's video is on there. I hope you guys can see mine. And if you can go to the next slide, please. So what are the trends in space? Cheaper to launch. I think while I'm not going to be able to reference particular companies that work commercially with NASA on this presentation, I think it's pretty clear to see that the growth in what's possible in space is growing exponentially. Really exciting times to be in the world of space in terms of the level of innovation and risk-taking and advances that we're seeing that really benefit all of us every day. Next slide, please. And so for NASA, at least, it's an evolution, not a revolution, starting all the way back from the Apollo missions, where actually you can argue that the simulators used in the Apollo program were probably the original digital twins. If you go to Wikipedia, there's a reference to that from the NASA folks. But really, being able to simulate what happens in real life is absolutely essential for safety, for product development, to make things better, right? And we see that digital twins or simulation have been used throughout these programs and have really made the difference, especially more and more as we get to the current generation and what's possible to do with the advances in computational power that we have at our fingertips today. You know, they had a very, very old Windows processor on the space shuttle. That's no comparison with the amount of compute power that's available on SpaceX Dragon today, and also the tools that are used to design these capabilities. It's really exciting to see some of the work that's been done in North America around new approaches for rocket launches. And that's not possible without the tools that we have today from Siemens and for other companies as well. NASA has some excellent computational fluid dynamics codes. We offer an entire suite of tools that are relatively easy to use in this domain, as do some other companies as well. Next slide, please. So yeah, it's an explosion of complexity that we want to be able to model, right? So here's an example of a rover. You've got to be able to conceive of all of those edge cases, all of those problems. And the last thing you want is a rover that doesn't work as planned when you get to deploy it. And obviously it's a one-time deal. So you've got to make sure that it's efficient, it's smart, it's completely autonomous and automated as much as possible, sustainable, so it can last for a long time without needing to be recycled. And so this is obviously very, very difficult to model. It's an explosion of complexity, but we have the tools at our fingertips to be able to do this. They exist today. Next slide, please. And I think we've already touched on some of the more classic problems from certainly early in my career around digital twins, which are, safety is paramount for anything that we do, but you're trying to avoid risk, improve quality, and of course, focus on costs, especially in commercial arenas, and obviously huge cost overruns in aerospace or in space programs is something we have to manage as well. So all of these things are really, I would call them classic challenges, but along with the complexity that we see exploding, we've got to keep an eye on these really important issues, which are really solved, I think, by digital twins in many cases. Next slide, please. So NASA loves simulation. There's just a few examples here of some of the work we've done in aerospace and space with NASA over the years. So clearly, flow and thermal are things that are really important, right, for spacecraft and aircraft of all kinds. We did quite a lot of work around the development of the Webb Space Telescope that was John mentioned earlier, to make sure that it's actually going to unfurl and actually work correctly in space. And we're now seeing some of those incredible images that are coming back. And perhaps a little more down to earth in terms of aerospace, as you can see on the bottom left there, work on experimental air brakes thrusters for jet engines. NASA's really been at the forefront of innovation in aerospace as well as space. And I'm pleased to say that we can help with the tools to create those digital twins. Next slide, please. So I already mentioned Siemens just in the introduction there. I would say that we love digital twins. We're a pretty big company globally. We've got more than 45,000 people here in the US and a lot of manufacturing sites. At the top left, you might recognize the wind turbines. We also do gas turbines, a lot in the power business, power distribution, managing the grid, as well as in transportation. So on the right, you see an example of one of our electrically powered trains on the right side there. But what I focus on and have done for most of my career with Siemens is actually in automating manufacturing with digital twins. So if you're familiar with the robot construction of cars, everything we do about car production today is completely done digitally, right up to the time that it goes through its crash test. And everything you see here on the bottom right with the robots, that's all modeled completely digitally before we ever operate a robot in real life, for many reasons, including safety, but also because we can be a lot more efficient. The example here is pretty much the same repeatable process every time. The challenge with digital twins is to be able to anticipate something that is going to be completely new or novel, and to be able to manage a robot to deal with that. So if you want to go to the next slide. So maybe just to relate a little bit of what I'm currently focused on with my team at Siemens is we are working on improving the quality of battery manufacturing, as well as autonomous recycling, right? So obviously a challenge is around fuel sources in the challenge. In this case, this is a much more down-to-earth example, right? So as we get more and more electric vehicles on the road or hybrids, there's a desire to recycle the critical minerals that exist inside these big battery packs, right? They contain a lot of minerals that we can reuse completely if we can get to them in a cost-effective manner. So we're using a lot of work with machine vision and AI to actually completely automate the process. So if you had the same battery pack every time, that would be super easy, right? From a robotics perspective to dismantle it. But when you've got battery packs that come from thousands of different things, it might even be, from your laptop or from a power tool, as well as electric vehicles, or even from stationary storage on the grid. How do you inspect that, use autonomous processes to deal with a novel battery pack that you may not have seen before? They carry a lot of energy, so how do you do that safely, discharge it, and dismantle it to get to the raw materials inside? It's a huge challenge that we're working with the Department of Energy on, and we expect to make really good progress by using digital twins in this example. All right, next slide, please. So just going back to the beginning of my career, just to maybe make it a little bit more tangible and again down to earth, right? You can think of digital twins for many things, right? And we talk about modeling the complexity. Just to give you an example, I started my career in movies, generating what we call digital doubles, where either it's impossible to make these people in real life, or it's too dangerous, right? We make digital stunt people all the time that do things that real stunt people would never do. But an example here is just from the first movie that most people recognize, I think from quite a long time ago now. Even back then, when our compute power was very limited compared to what it is today, in order to create Gollum from the Lord of the Rings movie, working with Andy Serkis, as I did, we actually had to build a complete digital twin of Gollum. So that goes all the way from the working skeletal structure through the muscles, as you can see there, through the fascia, through the fat layers, to the skin. Everything has to be modeled as close to physics as is possible. We've come a long way with compute power. So most of you will be familiar with what's sometimes called deepfakes, but the ability to use a computer to change people or age people, or in this case, de-age people, right? So pretty straightforward from a technology perspective to take Tom Hanks in the movie here that's just come out and make him a much younger person. And the reality is absolutely incredible. So we've come a long way, even from the very beginnings in my career of digital twins. Next slide, please. And to say that in manufacturing, probably the OG digital twin that sort of predates my career is actually doing crash testing. So as I said, all product development in vehicles is done virtually with digital twins. But then ultimately you've got to be able to prove that your car will function, or your vehicle will function in the way that's intended to, right? So the very last step before a car or vehicle is released is going through all of its certifications around the world. And this is when they actually compare those crash tests to what was anticipated by the vehicle manufacturer. Next slide, please. And here's another example that we work on that is somewhat more down to earth. This actually may not be very obvious, but this is a machine that's used to making the very latest computer chips that you'll find in your computers or your cell phones, right? The very, very highest levels of fidelity means that you can shrink those chips down, use less power to do more computing. So it's made by a company called ASML. They're a global company based out of Europe, but all of the chip manufacturers pretty much exclusively use hardware from ASML, right? These machines are like $150 million each, and they rely on very, very precise lithography to be able to craft those little images onto the wafers of silicon before they're turned into chips. And the analogy they use, which is not very difficult for NASA perhaps, but very difficult for ASML, is to do this very fast and very precisely, right? So it's 13.5 nanometers. And they use the analogy of shooting a laser from the moon and hitting a coin on the Earth, just for context, right? So it's a very hard problem to challenge, a whole problem to solve. And it's the kind of thing that we use digital twins for, in this case, specifically Siemens tools, but other tools do exist, to solve this problem, right? To design the machine and make sure that it works as advertised, and can do this when they have to manage things like the regular daily vibrations of the Earth, and making sure that they can compensate for that in the design of their manufacturing equipment. Next slide, please. So I'll just highlight on a few examples, really, because Siemens tools are very good at things like aerodynamics, combustion. It's perhaps not a surprise that our tools are used by commercial flight customers working with NASA or other agencies to develop their vehicles, right? And in this case, if you're familiar with the vectoring that happens on nozzles, they have to be developed in a way that is very, very accurate, and that they'll perform as advertised, not always, as you know, but in general, perform as advertised, right? So that we can fast track the development of these new vehicles, these new technologies. Next slide. So this is just an example of the work we do to simulate as a digital twin very, very complex combustion processes in that rocket plume. Fluid dynamics is an area where I've spent quite a lot of time. I'm not the expert in this area, so if any of the folks on this call are interested in learning more about this, you can go to the Siemens website, and I can connect you with Siemens experts that do this all the time. But it's really important to be able to simulate this. It looks great when we see rocket launches and the progress, very exponential progress quite quickly. But just remember that behind the scenes, everything to develop those products is done with a digital twin. Next slide, please. So just another few examples from space, specifically examples from NASA. So when you're thinking about a satellite, of course, many, many more of those are being developed now. There's a lot that goes into that, right? Way more than you would think, perhaps. Obviously, the loads and structural design, it's got to be lasting for a long, long time. Making sure that the deployment of those solar panels it works seamlessly, and there are no issues there. Any robotic arms and systems, you can see the list there, but the amount of work that's needed to develop these satellites is a lot, and it touches lots of different physics domains. The goal is to do all of those physical simulations to develop a very comprehensive digital twin of that satellite before it's built, so it's going to work as advertised, like the Webb telescope, first time, and will last for a long time. Next slide, please. So we've done some work with JPL on landing a lander onto Mars, right? So clearly we haven't been to Mars yet. You can only simulate that and provide a digital twin. So NASA have used the tools that Siemens provide in the case of developing the right lander that is going to survive getting down to the surface of Mars, and then obviously be able to deploy and work autonomously as much as possible for a significant period of time. Next slide, please. So you can see here some of the work that JPL have done to analyze the design, mechanical assembly. So in this case, we're focused on simulation in the mechanical realm, right, to make sure that it works on that surface of Mars. And it's essentially a robot, right? So trying to automate the robotics and make sure that it works in a way that it'll operate as designed when it's deployed. Next slide, please. We do a lot in propulsion, as I mentioned earlier, so I'm not going to dwell on this, but there's a tremendous amount that goes into that incredible amount of power that you see in rocket launches at the moment. So many things have to be modeled. Not everything works right the first time, right? So you can't get by without doing some actual testing in real life. But the goal is to get to something that will work as much as planned the first time, and then to be able to use simulation and digital twins to be able to refine that incrementally and get to the next launch and get to the next launch. So tremendous amount of work by lots of people behind the scenes at NASA and others to get to the point where you actually have those incredible launches that we see. Next slide, please. So maybe just a couple more examples. If this animation plays, you can just see how we simulate things like boosters being detached from a rocket. There's a tremendous amount of speed, power, and making sure that they maneuver and perform and are reusable as much as possible is really important. So there's a tremendous amount of time that's invested in doing these simulations so that we can actually operate them in real life. And for sure, you know, there are definitely challenges with like heat tiles, for example. Takes a lot of design both virtually and physically to get to the point where they work as advertised on these vehicles. Next slide, please. And I'll leave you with maybe one more from Goddard. So this is the Europa Clipper, right? But the goal here is to really make sure you're understanding the whole system of this particular vehicle. And so next slide, please. Where we start with that, this is a very busy slide. I think the slides will be available later, but just to give you an idea, this is system simulation, right? So we're looking at the entire vehicle in one high-level simulation. We call it 1D or system simulation, where you can simulate the entire flow of things like power and servos and all the capabilities within it. And then when you get down to a particular area that you really need to analyze in great detail, I'm not sure, an actuator here perhaps to expand the solar panels, then you can drill down much deeper into a full 3D or electromechanical simulation of those panels to see how they'll unfurl and then how they'll operate. Next slide, please. And I'll leave you with a quote, just like John did up at the beginning there. Von Braun has got some great quotes. But, you know, just for inspiration, I'd say we can lick gravity, right? It's solvable. And sometimes the paperwork is a bit overwhelming, but with digital twins, it becomes infinitely easier, right? An animation or a simulation is worth not 1,000 words, but, you know, millions of words. So hopefully this is great inspiration for you as you start on your journeys. Don't hesitate to reach out to me. Next slide, please. If you have any questions, we have a lot of people at Siemens that know way more about space than I do. And if you have any questions, feel free to ask them in the Q&A or follow up me offline.
Great. Thank you to all of our speakers. Really appreciate it. If you guys don't mind the speakers coming back so that we could answer some questions, I'm going to launch a quick poll while John starts to go through the questions and see what's there and what's not. I did notice there are a lot of questions on eligibility and the rules. We're not going to be able to cover those today. The ones that have not already been covered on our website in FAQs or in the rules, we will type written responses for and put them on our website as FAQs. But please do go to the website and review the rules and the FAQs because most of them are already answered there. So I'm going to hand it off to John to, we have about 15 minutes to answer some questions. Thank you to the speakers for already answering some in writing. So we appreciate that. And I'll hand it off to John to take it from here.
Hey, thank you, Chris. And thanks to our speakers, quite a august group of speakers that we had today. So I'm gonna hop around a little bit. I might direct a question to a particular speaker, or I may just put it out for the floor. And this first one, I think I'll put out for anyone to jump in. And Jan has actually already answered it. I did not know that when he answered it, it would go away, but I particularly liked it. So what, for everyone, what emerging technologies or trends do you foresee shaping the future of digital twins in the next 5 to 10 years for anybody?
So since everybody is reluctant, I'll start off here, John. So one of the issues that was mentioned was basically interoperability of digital twins. And at the Digital Twin Consortium, I have proposed that AI could be the answer to that. I mean, the issue of inexhaustible standards for bit-based systems is daunting, and we've kind of been on the idea of we're looking for standards, and quite frankly, you have to remember that nobody really wants a standard. They would just want a standard that does. I mean, nobody wants an airplane. They want to get from point A to point B. Well, nobody really wants a standard. They want to basically have interoperability, and so the ability of harnessing AI to, in essence, replace brute force programming or standards that I don't think can happen, I think is going to be an opportunity for that, for AI to do that. The natural habitat of AI is the digital world. And so the ability of them to be able to take, say, two different digital twins and understand the solution space that they occupy, I think is really our only opportunity to solve the digital twin interoperability problem. So I'm sort of anxious to pursue that approach to handling digital twin operability, because we're really going to need digital twin interoperability with this explosion of different digital twins coming about from different sources. And as I say, I don't think a standard, we may have macro standards, but a standard that says they're going to interoperate the same way physical things interoperate because of atoms, I don't think is a real possibility in my mind.
Yeah, and I would like to add a little bit to what Mike just said and actually amplify it. I would like us to get to a point where we can compose digital twins, so that whenever we're building a complex systems, we can just essentially grab, mix and match and put them all together and understand, well, what's the impact of all of this? But in addition to interoperability, what does it mean to compose something? Especially when you're dealing with two nonlinear systems and they're interacting with their environment, with other components across multiple physics. And I believe that's one of the open challenges. And we need to develop some new math, some new ideas, or potentially think more in a computer science sense, instead of, let's say, trying to compose two digital twin objects. Maybe they need to be recompiled into a combined digital twin. So I would like to use the imagination of the community to come up with that particular solution.
Yeah, I think those are really good answers. Within these individual areas, AI, virtual reality, Internet of Things, computational fluid, just name the tool area that you most subscribe to. For me, like on the chart that I showed for the NASA foundational tools, something has to assimilate all those into the complete picture. And I think that's the digital twin. And so interoperability, along with the advancement, of AI. Mike Greaves and I were chatting about a new tool, this notebook tool where you can put information in and it creates an AI podcast with, AI speakers. The technologies are individual technologies are, I mean, they are advancing so fast that even those of us that are in this area are surprised sometimes. So I had a question, not in the chat. I had written down a few of my own, and it was prompted by the crash testing. I use crash testing. I've heard Mike use crash testing as an analogy for how we might apply a digital twin. Is there and it goes to this point of having a physical counterpart. Is there a point in the future where we don't have to do crash testing of an actual automobile? Can we do that? By the way, and it's my opinion that when you test something that's as complex as a crash test, it doesn't. Y'all know it doesn't exactly, correspond to the test that you were planning anyway, and so the test is not perfect. What do you think about that? Can we avoid those expensive physical tests in the future entirely?
I'll just quickly chime in. I think we will eventually get there. I think one of the other open challenges we have really not talked about in this forum is the impact of materials. So we know a lot about materials, but I don't think we really know enough about material, especially when it pertains to, let's say, extreme events, explosions, crashing. Those are very difficult to model. Those are highly nonlinear events. And we have a lot of data around a lot of materials we know, but as soon as you start 3D printing some of these things, can we currently fully characterize all of those? And I think the answer is no. So I think another challenge is, how do we understand materials better as it pertains to all the different kinds of testing and all the different kinds of environments that they may be exposed to? So anyway, I think we will get there, but we're not quite there yet.
Yeah, maybe just to add to that, obviously we do a lot of work with automotive companies in product design today, and it's clear that you can model almost everything. There is some, maybe you call it uncertainty, right? You have to quantify for those crashes. But the reason that we do that, or they do that for certification, is so that at the end of the day, you can guarantee it's going to do what it's supposed to do, right? And so it's really a proof point. Before you have any vehicles on the road where you might have that proof point, but you wouldn't want to have it with passengers inside for the first time. So there is a lot of value still in developing, we'll call them prototypes, small scale versions of the final thing. It's very difficult in a space context to do that, right? But NASA have been striving to do that as much as possible. And ultimately, I think it's a mix of the virtual and the real. But it's clear that it's not necessary. You could say if we have the right digital twins, it shouldn't be necessary at all. But we've got to be able to prove everything that our digital twin really works the way that it should, right?
Yeah, another challenge I would like to bring forward is multiphysics. So this is another study I did whenever I was DARPA and actually had a program. This is the DoD as well as space tends to push the limits of what we know. And so as soon as you start going into multiphysics, where you have highly interacting physics, so if you think about a re-entry vehicle, it comes in at hypersonic speeds. It creates plasma. There is interaction. It actually changes the chemistry around the vehicle as it comes in. There are like hundreds of chemical species. There are acoustic problems. And trying to simulate those extreme events in full accuracy, I think we're not there yet. And we still need to invest more in these kind of simulation, or think about different ways in which we can address simulating these really highly complex multi-physics. We're talking 3, 4, many more types of physics that are highly coupled and highly interacting. So I believe there's more work to be done there.
So that brings me to a question that sort of corresponds to the video that I showed of the ship bouncing around in the ocean. The physics of that is extremely complex. But you can certainly get loads on the, if you're trying to design a ship. And so that brings me to the question of, what is good enough in this, some of this physics we will almost never be able to tackle. And so what is good enough? And I don't know if that's a question, but if anybody has a comment to that, I'd be glad to hear it.
Well,
so I
maybe
think hang on.
Go ahead, Michael.
I think that that you're getting to the point where you have the previous discussion, which is the fact that physical testing never is exhaustive. I mean, the thing is that you're only doing it as a proxy for the physical test you do. You can only afford to crash so many cars. I mean, quite frankly, the only way to know whether a product really is going to do it is to crash test the vehicle every time that you're going to sell. You can't sell very many of them. So so the whole idea of physical testing as a proxy for performing, and I heard the word guarantee, you know, the recalls that we have on vehicles says we ain't guaranteeing anything with respect to this. So I think you can do far more testing virtually than you can ever do physically. And in point of fact, you know, you only do crash tests at certain orientations. You can do crash tests at every orientation of the sphere if you really wanted to, at a fraction of the cost of your current physical testing. So I think the thing is that we are getting good enough in terms of this kind of capability that I think we're doing physical testing only because of how we've done it in the past, as opposed to looking at, do we do a physical test? Do we do a virtual test? I think you have to validate your testing. So my premise is that all testing will be done digitally, but you'll do 1 or 2 tests in terms of to validate your testing, but that's the only requirement. So I'm very bullish on the fact that we've made huge progress. And in point of fact, I think 5-10 years ago, you looked at the crash testing and the crumple zones did match up pretty damn well. So I'm very bullish on it. When we get into additive manufacturing, you know, I published a paper that said, you know, we could test every product that we made in additive manufacturing if we tested its digital twin to destruction. That would give us a great feel for what the physical one was going to do. So I think that there is an opportunity to use virtual testing, digital twin testing, to replace physical testing.
Yeah, I completely agree. And I was maybe going to add to it, since your example, John, was you know, a visual representation. It used to be that we would take tremendous shortcuts that you couldn't do in product development, in movie and visual effects, right? Because it's just got to be believable. But the reality today is that it's not believable unless it's based on physics, right? So the computational power and the engines we have for creating those virtual worlds is almost unimaginable, right? The incremental improvement we made in those areas. So, you know, to actually simulate that ship in that world and see how its seaworthiness is well within our capabilities, right? We do that all the time. We use a lot of simulation for seaworthiness testing to avoid sinking and damage in rough seas, for example. That's a given, right? It doesn't mean we don't build scale models of that vessel and put it into tow tanks, but actually we do a lot in virtual tow tanks because you can test a lot more that way and make a much safer vessel. So yeah, you can get away with things in the visual realm because our eyes can only resolve so much. But the reality is that the brain, it's hard to deceive the brain that much, right? So you've got to try to work towards physical simulations, which is where they are in the movie industry.
Hey, Mark, there's a question I want to dispose of that's directed, I think, at your model, and it says, for the data flow between virtual and real systems, do you believe that there should be a time limit in the definition? Should this be, well, the questions keep jumping around. Let's see, should this be real-time data flow or offline data flow?
So again, we drive every digital twin from use case. So if you have airbags going off, you want it real time. If you're looking at the oil life in a car, you don't need it to be real time. So the time cadence is really dependent on the use case. And I don't think you can say, hey, I want real time data everything if there's no use case that drives that.
So I jumped on because unfortunately we only have about 1 more minute left for Q&A, and I'm really sorry because this is a great conversation. Is there any last comment that any of the speakers want to make? I guess we could have given 3 hours to this webinar, but any last comments?
The thing I wanted to emphasize is imagination, and that's what I showed in that video about from the museum. I think digital twins are only limited by your imagination now and certainly in the future.
Yeah, I'd echo that as well. The advances in AI and computation have made a lot of these tools available to everyone. And I would encourage you to just get out there, experiment, and see what you can do with these digital twins, because you'll be incredibly surprised about what was possible.
Yeah, I'll just say thanks to Mike and Jan and Keith for their participation today. I thought it was a fantastic discussion.
Great. Thank you, everybody.
Thanks,
So
Chris.
apologies
Thank
again
you.
that we didn't have enough time for the Q&A, but hopefully this gave you a flavor of what's possible and what we can do with digital twins. I know it was like drinking from a fire hose, so please know that we are going to post these this recording on the LunaRecycle website, which you can see here. So now we want to end you with a call to action. So we want you to get involved. So please visit the challenge website. That's where you will find all information about the challenge that exists. On that website, you can sign up for updates. We'll let you know when we can begin to accept official registrations. Please review the challenge rules and submission templates. These will tell you exactly what you need to do to be eligible and to participate and to hopefully win. And then if you have any questions, please reach out to us at lunarecycle@ua.edu. That's the official email address for the website. If you contact any of us individually on the topic of rules or eligibility, we will not be able to answer them. Only send it to that. That's the only place we can answer questions. I do know that some of these speakers gave their email addresses for you to ask questions on digital twins. Please feel free to use that on that, but not on rules or eligibility. And then next week, we have another webinar coming up. This one is much more general on NASA's approach to sustainability and managing waste on the moon and on long-term missions, with a terrestrial link to it. So you can register for that on the Luna Recycle website, again at lunarecyclechallenge.ua.edu. And then if you have the chance, please do share some information about the challenge with friends and colleagues, and do stay connected with us on social media. So we want to say thank you to all those that stuck with us. Again, apologies for extending the time today. If we had it to do over again, we would have made it 2 hours. So we thank you for your time, and we thank all these wonderful panelists. I know they can't hear you clapping, but I know you're clapping in the background with your thanks. So thank you all. This concludes our webinar for today.